All right, kiddos, we're going to do our last vodcast for, at least for the CP class. This will be your last vodcast for Unit 6 on bonding, and it's a pretty short one. This is on polarity. And so we're just going to talk, won't take very long, but it ties in directly to the shape stuff that we talked about yesterday. If you remember early on in your notes, when we started talking about bonding, we had this little diagram. And so you probably have it in your notes already. If you don't, you might want to copy that down real quick. But basically it just says that as the electronegativity difference increases, okay, that if it's a really big difference, we have ionic compounds. And we kind of know that anyway because we've got metals on the left-hand side of the table and we've got nonmetals on the right-hand side. And so if we've got a metal and a nonmetal, we have ionic, so big difference. If there's an equal sharing of electrons, so like we've got two fluorines or two oxygens bonded together, then we've got a nonpolar covalent bond. Okay, nonmetals are covalent bonds. But what we mentioned is that a lot of times we have an unequal sharing, okay? That sometimes, because there's an electronegativity difference, that they don't share the electrons equally. So, for instance, if we had something like an oxygen bonded to a fluorine, okay, now this wouldn't be the only bond, it's not a full thing, but if that was the case, fluorine has a higher electronegativity than oxygen, particularly, and actually, let me make this an even better example. If we had a carbon bonded to a fluorine, there's a pretty big electronegativity difference between them, and that means that these shared electrons in the middle are shared more by the fluorine. The fluorine's going to get a bigger share. Kind of like if we had a piece of pizza or a big pizza and we said, okay, I'm going to share this with you, and I took 7 pieces and you took 1. Technically we shared them, but I got a much bigger share. And that's what's going on here with the fluorine. It's getting a much bigger share than the carbon is. So that's what polar covalent means. Okay. Now it's called polar because when this happens, we get a negative end over here and a positive end over here. Okay. And technically speaking, it's really a slight positive. That little weird symbol that means slightly positive and slightly negative on each end of those bonds. Okay, so that's what polarity is. Now, how do we figure it out? Well, I mean, it's on your table. So the table that we used, the same table that we used yesterday to find shapes, you could use that same table to find polarity. Okay, and so you could sort of memorize what the matchups are. I mean, there's only 6 matchups here, and so you could just memorize the shapes and the polarity, and that would be relatively easy. And you can certainly do that, and you'll come out well on the test. But really, there are 2 things to look for when you're trying to determine polarity, okay? And so the 2 things are, we're looking for non-bonding pairs, okay? Or remember that we've called those lone pairs, okay? So that's the first thing that we're kind of looking for. The second thing that we want to look for is something called symmetry. Now, you've probably heard the term symmetry before. Okay, I seriously doubt that that is anything terribly new. But what symmetry means for us in this case, okay, what symmetry means for us is that if I have an object, can I divide it in 2 and it's the same on both sides? Okay, so just as a quick example, if we drew a methane molecule, now, granted, remember we talked yesterday that these are 3-dimensional shapes, they don't look just like the 2-dimensional shapes that were drawn. But if I had this methane molecule, I could basically sort of cut it in half any way, okay? I could cut it down this way or down this way. Whatever way I cut it, it's the same on either side, okay? So the symmetry thing is pretty important for us. If they exhibit symmetry, if they're the same on every side, like same molecules and everything, then they're not going to be polar. And chances are, if they have, the other way that we can tell a lot is that if they're non-bonding pairs, then there's usually a pretty good chance of polarity. If you look back at the table, 1 non-bonding pair, it's polar. 1 non-bonding pair, it's polar. 2 non-bonding pairs, it's polar. Okay, so when you draw your Lewis structure and you get non-bonding pairs, that's a pretty good chance that it's polar. Not always, but a pretty good chance. Okay, so to look at this, let's real quick, we're going to just do a couple of quick examples so you can see how this works. So our water molecule, if you remember, we drew this yesterday. in its flat shape, it looks sort of like this. Okay, we've got an oxygen in the middle, 2 hydrogens, and 2 non-bonding pairs. Okay, and we looked at the table, and so we said, okay, I've got 2 bonding, okay, and 2 non-bonding. Okay, so that tells us something pretty important. That tells us what the shape is. So we saw yesterday that the shape there is going to be bent, okay? But it also tells us something about the polarity, and here's the way it works. Obviously, we could just look on the table and we see that this is a polar molecule. But, I mean, here's sort of the way that we could tell. If I divide the water in half, well, if I divide it this way, then great. This side is equal to that side, right? That works out pretty well. But if I divide it basically any other way, so like I divide it down this way, this side not the same as this side. Divide it this way. This side not the same as this side. So I don't have very good symmetry. So I have non-bonding pairs, and I don't have symmetry in every direction. Okay, that every direction thing is pretty important there. So that means that water is a polar molecule. Okay, let's do one more real quick. Let's do ammonia, and this is again is one that we did the other day. So I've got nitrogen, okay, 3 hydrogens, and a non-bonding pair. Now again, that non-bonding pair sort of tells me, okay, pretty likely probably, but just to go back to the shape thing, I've got 3 bonding pairs, 1 non-bonding. Again, if you see non-bonding, you should start to suspect that it's polar, okay? And then we look at the symmetry. Now, symmetry-wise, if I cut it in half this way, we're fine, right? Okay, it's symmetrical. But if I cut it in half this way, or any of that, it's not symmetrical. And it helps, again, if you look at these things, and if you look at the webcam real quick, if you look at the molecules themselves, so if we jump back to the water here, okay, you can tell that if there's a difference in electronegativity, so the oxygen here has a much greater electronegativity than the hydrogens, then we're going to have some sort of polarity, and it's not canceled out, okay, meaning that it's not symmetrical. Okay, it's symmetrical if I cut it in half this way, or if I cut it this way. Okay, it's not. Or if I cut it right here, not symmetrical. So it has to be symmetrical all the way through. We can see the same thing if we look at our, just real briefly here, if we look at our ammonia molecule, okay, not going to be symmetrical, okay, it's going to have the negative end, the electronegative part, the nitrogen, is on the opposite end from all of the stuff that is lower electronegativity, which would be the hydrogens in this case. So you want to look for non-bonding pairs, and remember in the case of this ammonia, there's a non-bonding pair right there. You want to look at non-bonding pairs and symmetry, and if you have non-bonding pairs and you don't have symmetry, okay, in all directions, then you are likely going to have a polar molecule. Now there's a little bit more to it than that, and if you take some higher chem classes, we'll talk a lot more about that, but that's really all you guys need to know at this point is look for the non-bonding pairs and look for symmetry. Okay, so you're still going to have to draw it out. You need to know the shape, okay, which is the stuff we did yesterday. But from there, polarity usually pretty easy to get. All right, thanks again, guys.